just a short announcement before lunch, so right after the last talk of this morning, we're going to take a conference session. So just don't run away. Okay, and so now back to Matt. It's a big pleasure to have here virtually Karin Baur from Ruhr-Universität Bochum, who is going to tell us about surface combinatorics for categories of modules. Please, Karin.
Okay, thank you very much. And thanks for making this possible. Yeah, well, I know the text is a little bit small, but that's only copying the abstract for my sake. So, yeah, I want to talk about geometric constructions for algebras, specifically for gentle algebras and string algebras. And first, I will explain what I mean by string algebra. So we start with a finite dimensional algebra over an algebraically closed field. So I can give it as a path algebra modulo an admissible ideal. And this ideal should be generated by paths of length at least 2. We will see some examples soon. Yeah. And I will write Q0 for the vertices and Q1 for the arrows. So such a algebra lambda is a string algebra if we have a finite quiver, and if whenever we look at the vertex, say V, we have at most 2 incoming and at most 2 outgoing arrows. Sorry. At most 2 incoming and at most 2 outgoing arrows. So some of these UIs might coincide. So some of the neighbors might be. So you don't have to have 4 neighbors even if you have all 4 arrows. So that's what we need for this condition S, and we also need something for the arrows. So for any arrow A, there is at most arrow you can pre-compose it, and at most 1 arrow you can post-compose it, which is not in the relations. So there is at most 1 arrow. Sorry. This should be 2, B or C, with BA not in the ideal or AC not in the ideal. So it is relatively restricted locally. Yeah, so that's the condition S for string. Then we can impose a bit more and we call lambda gentle in that case. So there's condition G. I is generated by path of length 2. So in string algebras, you might have longer paths for the ideal, and we will have an example very soon. And then also at any for any arrow, you have a dual condition to the one in S. For any arrow, there exists at most 1 arrow, yes, such that the composition is in the ideal. So for gentle, we also want at most these relations and not more. Okay. Then there's also the notion of a locally gentle algebra that I need a little bit later. So that's S and G hold, but we allow the algebra to be infinite dimensional. So there might be some paths which are never forbidden. These 3 types of algebras give a large family of algebras whose module categories we understand and are well known. So let me just mention a few results. The indecomposable lambda modules are string modules. Let's say indecomposable. or band modules. So a string is a word in the arrows and in the inverse arrows. So you formally add inverses of arrows, and there are some conditions. You don't want to have a subword which is trivial. So you shouldn't do something, redundantly, doing A and its inverse directly. And you also don't want to take subwords which would be killed by the relations. So no subword. BC for BC in the relations. Then band modules so bands are also strings, but they're cyclic. So you sort of write some letters A, B, C, and in the end, where A starts, it's the same where C ends. So they're coming from cyclic strings. And some parameters. Today we will not really have any band modules. Then there are so homomorphisms are understood as underwritten sequences are characterized. So you know nice short exact sequences. That's also from the 80s. And you can describe the morphisms and the extensions, all on the algebraic side. Okay, but these algebras are amenable to surface construction. So let's first look at an example and then have this remark. So this is a quiver which satisfies these conditions at any vertex you have at most, say, 2 outgoing and at most 2 incoming. And then I chose different types of ideals. So I1 is generated by setting dE to be 0 and dA. And then there's this longer relation, ABC. Well, this cannot be gentle because around 1 we have too many relations. So but it is a string algebra. So it gives a string algebra. Then the second one, I only kill this composition, dE, which means that there is an infinite, well, there's arbitrary length path here, and that algebra will be infinite dimensional. So that is locally gentle. And the last one is really a gentle algebra. And I mean, I really mean KQ, not the ideal in all these examples. So this is our running example, or one of them, this quiver with, say, this set of relations for a string algebra. You could remove that one and it's still a string algebra because the problem was locally here. The first problem, the other problem was that you have a generator which is too long. Yeah. Now, the remark why it is amenable to surface constructions is this local condition that you have at most degree 4 at every vertex. So you have at most 4 vertices. And that makes it amenable to surface constructions, as we see relatively soon. So the idea is you take some oriented surface, divide it with arcs, and you get tiles. So here's a tile T, and here's a tile T prime. And they will have common edges or arcs. So, and we want the arcs to be the vertices in a quiver. So that sort of means this vertex here has at most 4 neighbors, namely arcs in the other tiles. And I should say what the arrows are. They come from angles in tiles. So if I look at the tile, there are these angles, and I choose an orientation, and I draw an arrow. Yeah. Okay, well, we also need, so the relations, composition of any 2 arrows in tile is 0. So whenever you are inside a tile, you're not really allowed to compose 2 arrows that will be sent to 0. But these are just the relations for G. And then we'll have to do a little bit more to give you the relations for S, but that's the idea to keep in mind. So let's see what a tiled surface is. We start with a connected oriented surface, S. And we want a set of points in the surface. This should be a finite set in general, but there are also infinite sets being considered in, say, infinite rank cluster algebras. But for me, it's finite. Then I distinguish, like I put this marked set into 3 different types. On the boundary, so I need one more condition. Every connected component of the boundary of S meets M. So there should be at least 1 point of M on every connected component. There can be some points in the interior as well. So these are on the boundary, and these are called punctures in the interior of the surface. Okay, well, there are these colors. I don't know whether you see that well, but my points, the punctures always are red and filled out. On the boundary, we have red filled out and circles not filled. The arcs can connect red points or these empty circles, and then I call them red arcs or circle arcs. So I want both endpoints to be of the same type. Yeah, arcs are non-contractible. Curves with endpoints in N. So there are different conventions here, and also in different collaborations, I use different conventions. Today I use red arcs and the circle arcs because it makes it easier to describe indecomposable modules. If you don't do that, you have to take equivalence classes of modules, equivalence classes of arcs, which give you the same modules. And we do all this up to homotopy fixing endpoints. Yeah, so then a tiling of the surface is a collection of simple red arcs. Simple meaning I don't want this arc to intersect itself, but it might have endpoints which are at the same vertex. Which are pairwise compatible, that means they don't intersect each other. Again, we are looking up to homotopy, so you can draw it as tidy as possible, then there should be no intersections. And they divide S into polygonal pieces. Each containing exactly one circle point. So either your polygonal piece has arcs which are never on the boundary and all its endpoints are just red. And then you have to have a circle inside. Or you can have one segment on the boundary, then you have to have this circle here. And the red are the red points. The rest is the red points, so the rest are arcs. Say gamma 1, gamma 2 up to gamma m, or here gamma 1 up to gamma m. M is always at least 1. So I should say these points alternate. So that means also every contacted component of the boundary has an even number of points in M, split into the red arcs and the circle arcs. So we can use that to define a quiver and an ideal, as illustrated a little bit earlier. So the vertices are the arcs in T. Arrows are from angles in tiles. As illustrated on the right, and then the ideal is composition of two arrows in a tile should be a generator of this ideal. Okay, we're still not at the string algebra. This is only the gentle relations, but let's look at an example. So this surface is an annulus. It has two boundaries, two connected components of the boundary. And I drew 5 arcs, and each piece has an empty circle on the boundary. Here there are no punctures. And then the quiver should look as follows. Just going to draw it first and then illustrate on the surface. So there is an angle from 5 to 1, there's an angle from 2 to 1, then there's an angle from 5 to 2. So these are these 3. And then there are 2 more from 3 to 2 and from 3 to 4. Now there should be, we have to look at the relations, there's only one really tile where we can compose 2 arrows in a tile. That's this strange tile involving both boundaries. If we first do 5 to 2, then 2 to 1, that's a composition of 2 arrows in the tile, so there should be a relation here. And that just indicated by the dotted line. So yeah, this looks okay. This should be a gentle algebra, and that was in my first paper with Raquel. We characterize gentle algebras as the ones which you can obtain this way. So such an algebra, lambda is gentle if and only if you can write it as a tiling algebra for some marked surface. To get that, we used the construction of Oppe, Plamondon-Schroll, who looked at the Brouwer graph of the algebra and embed it in a surface. Okay. Now, 2 remarks here. So one is because we assumed that every connected component of the boundary has vertices, we could complete that to a triangulation. Well, I said we could because it's a little bit complicated with the red and white points or circle points, but so up to dealing. And then this kind of algebras has been considered before. I mean, similarly has been used in Fomin-Shapiro-Thurston's construction of cluster algebras from surfaces and gives you some Jacobian algebra of the triangulation. And this is gentle by the work of Assem-Brüsselet, Charbonneau, Jodoin, and Plamondon. So that's earlier work. Okay. Then, okay, I hope you can't really see that well. So here I said we can characterize gentle algebras, but we do more. We also describe the module categories. So we describe the module categories in terms of permissible arcs. So what do? We take arcs now which connect the empty circles, and they have to cross your original tiling in an allowed way. That's why permissible, meaning that I'm not, let me do a bigger tile. So if I have some tile like that, say all interior, I'm not allowed to cross non-adjacent edges of a tile. Because if you think about it, the module you would get from composing all the arrows in the quiver, but to get from here to here, you would have to compose this arrow with that arrow. And that was in the ideal, so that becomes 0. So we can describe the module categories. String modules are permissible arcs with endpoints in the circles. And then band modules are permissible closed curves. But yeah, then the question is, what about string algebras? We have more relations in general, and we can still use the surface construction to describe or construct them. And what we do is we look at the additional relations, say, on the quiver, and indicate them as labels in the surface. So we add labels to the tiling. Okay. So as before, let's assume lambda now is a string algebra, and we, for the moment, forget that it's a string algebra. We take the surface for a gentle algebra, do a tiling, and then we have to add the labels, basically. So once we have labels, I'm going to explain exactly how you get them. This gives you additional relations. So we have the ones from the gentle part, but then we also have to take the path which are coming from a label. And I wrote 2 labels here, L1 and L2. What are labels? So first of, yeah, they should cross at least 3 arcs, or like should have at least 3 crossings, because in the end I want to compose the arrows traversed, and since the labels correspond to path of length at least 2, I need to have at least 3 crossings. So here I have a longer label with S arrows. Here I only have 2 arcs, so I have 1, 2, 3 arrows, say A, B, A. Okay, we will see an example relatively soon. They should pairwise be non-redundant. This is not really necessary, but I just want to throw away non-necessary labels. For example, if I look at this one, there could be a sublabel, and then I would not take the big one because it's already generated by the sublabel. So we don't want one contained in the other. It's not forbidden, but it doesn't really add anything. Okay, then we can characterize string algebras. So lambda is a string algebra if and only if I can write lambda as KQT mod IT with labels for some tiled surface with L, and at every puncture exists a label. That's to assure that it's finite dimensional, or lambda is a quotient of a gentle algebra. So it's not quite gentle, it's locally gentle. R and the relations are generated by path of length at least 2. And there's one more condition. And every oriented cycle of Qt has a relation. Okay, well, that sounds a bit complicated. So we can write lambda as a quotient of a locally gentle algebra. That means these relations here are generated by path of length 2. But there might be some path of larger length. So R is only required to consist of path of length at least 2. Now, if this is infinite dimensional, we need to kill, we need to make it finite dimensional. That's the last condition. Okay. So then, what's the idea? Well, we start with the gentle algebra and we remove first all the relations coming from path of length 3. So remove all relations of the idea how to see this part. Yeah, we had to remove them. But then there are some other relations which are length 2, but were too many at the vertex, like when we didn't satisfy the gentle assumption. So we have to remove this, these extra relations. And let me call it non-gentle vertices. The vertices which had too many relations. And this gives you B. Yeah. And then this is potentially infinite dimensional, so it's locally gentle, but you can use the construction from BCS, OPS, Plamondon-Schroll, and Bilot, Palu, Plamondon, to get the surface with a tiling. And in the end, you have to add labels for all the relations that you had removed. So that's the idea how you show that this is true. This is not unique in general because there was a choice involved. And we will see this on the running example. So this string algebra, we had the long relations. This has to be removed immediately, but then we had too many relations at one. So we can either remove DE or DA. And here we removed which one? Sorry. DE and remove DA. So then hopefully you see here I have an annulus. There are arcs 1, 2, 3, 4, and 5. They will give you this quiver. There is one internal tile which gives you a relation DA. So that's the one that we didn't remove. And to make it complete, in the end, we have to add the labels. One for ABC. So that would be 1, 2, 3, 4. And then one for DE, which is 4, 1, 5. And that's here. On the other hand, if I remove DA, it became locally gentle, infinite dimensional. And then I have to add the labels at the end. So now I'm just copying from my notes. DA and ABC. So these two surfaces are for sure not homotopic or like homeomorphic. One of them has a puncture and one has two connected components in the boundary. Okay, let's continue. Do I have 5 more minutes?
Or need more even because it's such a little.
Okay, I didn't hear everything, but that means I have at least 5 minutes. That's good.
More than 5 minutes.
Okay, thanks. So this surface is not unique because it depended on the choices in step 1b. Whenever we have a vertex which had too many relations, we have a choice which ones we remove. Well, the question comes, what can we say about the different geometric realizations? Can we find an operation between them? At some point, Raquel and I thought we could define some rotation on a collection of tiles, but already that example shows it doesn't quite work because if we rotate tiles, we don't get an extra boundary component. Yeah. And we have examples where the two algebras B that you get, B and B prime, are not even derived equivalent, like the gentle algebras, before you take the quotient again. So this is work with Raquel Coelho-Simoes and Benjamin Dequesne. Yeah, there is recent work of 2 students of Wen Chang who gave a characterization of when the surface is unique. and they have a condition on the vertices. So if a vertex is not gentle, it has to satisfy three local conditions. Basically, you look at the four neighbors, they might give you four subquivers, and two of them have to be symmetric, pairwise. And there are some conditions about not being connected. So that looks nice, but in general, there are still a lot of questions open about that. And in the last part, I want to restrict again to gentle algebras and explain how we can use the surface model to describe tau reduction. So this is work in progress with Wen Chang and Eric Hansen. If we have a gentle algebra, there are some specific special indecomposable modules, the tau rigid indecomposable modules, and they can be used to go from a module category to a smaller module category by doing some reduction. I mean, if you don't know what tau rigid means, I mean, I can write it's basically a rigid module, so you can't really deform it with some extra conditions. So tau rigid implies rigid. And if we have such a tau rigid indecomposable, you can define a subcategory, which I call P here, P of n, which is taking, yeah, I should have written that out. N perp intersect with perp n tau. That's not totally obvious what that means. So n perp are the modules which have no HOMs going out. Sorry, n. Which cannot be reached from n. And then on the other side, perpendicular. If we don't get to tau n. So you sort of kill a lot of modules. And what Gustavo Yasso showed is that if you take this subcategory, this is also a module category. That's not obvious. For again, for a gentle algebra, which has just one less vertices. So if you take the quiver, you sort of get another quiver which has one vertex less. You don't just kill a vertex in the quiver, it's a bit more complicated, unless your module n is maybe a simple. Okay, so then the question is, can we use the surface combinatorics to describe this perpendicular subcategory P of n? So to do that, we had to figure out what exactly the tau rigid modules correspond to in the surface. So we want to characterize the arcs for tau rigid modules. Again, we take a permissible arc. It should never cross non-adjacent arcs of a tile. And then alpha is rigid if its module is rigid, and it's tau rigid if M alpha is tau rigid. So you just call the surface by the corresponding property of the module. Yeah. So then we can characterize tau rigid arcs, or the arcs which give you tau rigid modules. So, okay, and this is going to be a little bit technical. So we want that the curve is rigid because I said tau rigid is stronger than rigid. That means it's simple, doesn't intersect itself. And if it's a loop, we have to do some extra conditions, which I skip here. Then for the tau rigidness, we have to make sure, So there are two curves that you can associate to alpha, which correspond to adding a hook or removing a co-hook to the module. These curves are corresponding to direct or inverse modules to arise as this hook or co-hook construction. And we say that at most one of them is equal to alpha. Sometimes one of them is equal to alpha itself. And these curves shouldn't really intersect alpha. So I don't want to go into much details, but there is some gamma 1 here and some gamma 2. And then you construct tau alpha by connecting these. Okay. But we could use that to show that, in fact, tau-rigid arcs have at most two intersections with their tau. So that's good. I mean, it's bad that there can be two. That makes things complicated, but it's bounded by two. So for the rest, I will assume that we look at the case where there's only one interior intersection or they meet at the boundary. Sometimes they don't really intersect like that. Sometimes tau alpha goes back to the same point at one end. And then we can describe the surface associated to this reduction. To get alpha, to get the lambda prime, or we can cut along the ribbon of alpha tau alpha. Okay, I'm almost done, sorry. Just going to illustrate that with an example or like with a picture. So locally you have alpha and tau alpha. What you do is you draw the ribbon, which is fattening everything up. Then you have to modify the endpoints because you see I might have too many black circles now. We have to add some red points to make everything work, but it's specifically explained from the directions between alpha or from the HOMs. So we add red points, we cut everything out, and that gives you a new surface. And in the last step, you have to fix what happened with the tiling. So just one example. So I had this very small algebra, type A3, and I have the modules 3,2 and 2,1. Then I cut along the ribbon. I get 4 individual pieces for the surface. There are some parts which are trivial because they don't have enough mark points. So I only have 2 connected components of the surface. In the step 5, I have to see what happened with the tiling they given me the algebra. Well, these arcs 1, 2, 3, they all have to end at another red point. So this gives me a single arc. And on the other side, I have a single arc. So I have 2 surfaces which are quadrilaterals. That means I have A1 cross A1, and that's my new module category. So, and I can just leave that here. And thank you very much.
Thank you very much. Any question or comment? No. We thank Karin again.